Fuel tank, yeah, fuel tank. That's not in your house, but that's a good point. That's not in your house, but that's a good point. Yeah, I didn't think. Toilet, yeah, the tank on the toilet, it's got a level sensor on it. Anything else? No, those are not level. There's a lot of sensors on the air conditioning system, especially I have what they call a combo unit. So I have air conditioner and then my gas heat is on there. So there's a lot of sensors. You know, you put a lot of sensors you should have a lot of sensors when you start dealing with gas heat. Most washing machines have level sensors on them. Ice machine is usually timed. So it's a little timer on there that runs the ice machine. That's a good point. But why do I know that? Because I've had I've had ice machines apart before.
No, ice machine little piece that pushes in. Like on my machine, I have a little arm that
yeah, when you
on the ice is, it starts pushing it in. Once it
fills up, it stops. So that should be.
Well, everyone I've seen, it might be, but like I said, not ice machines, ice makers inside the refrigerator. The only ones I've seen is time.
Yeah.
And usually you can pop the front cover off and adjust the time a little bit so they don't overfill. But there might be. But there's quite a few level sensors, right? So level sensors.
For a dishwasher, a level sensor?
Mine's got a float on it. So it's a level sensor. So it's down at the bottom. I don't know if on mine you can see it when you open it up. It's a little round thing down there. And what it does, it literally opens up yeah, that's definitely a level sensor. That's basically the kind that we're going to use. A device capable of responding, of course, we know what a sensor is now, right? So has this been on test yet? Should be. Of course, position, we've already looked at. Speed, we've looked at. Weight, we've looked at. We've looked at proximity sensors, and so we'll over here look at our level. Now, I think I told you at the start of the class the ones we're going to look at, right? The ones that we have. Of course, time. You're already on the third lab. You're already using a timer, so that would be something that senses the amount of time that passes, right? Of course, we don't usually consider that to be a time sensor, but this is just what some people came up with. So distance is the amount of space between two objects. Level is the amount of vertical distance, height from the ground in those states of understood base. So the distance, height of different types of material where they actually intersect. Okay, here. Yes. Ultrasonic sensors. Anybody been involved or seen ultrasonic sensors? Some examples of these. Hospital, yeah, they're always in hospital.
So they put on like a warm stomach?
A warm stomach, that's ultrasonic. To see what's going on. They did a lot with me because I was laid up so long on my back, and they wanted to make sure I didn't have any blood clots. So they did the same thing. They did the ultrasonic on me. But what you're doing is you're looking at distance and reflection, right? How it reflects. Measures the interval between a sending and the echo. So we see this a lot, ultrasonics, radars use basically the exact same principle, right? We can do light. The police have got away from using radar because you can pick up radar on radar detectors, so they've gone to laser. So they shoot a beam at you, and they're actually measuring the amount of time. So it's a diffuse sensor, right? How long it takes to reflect back. Sound waves transmitted and receivers. So we got to have a transmitter. We got to have a receiver. These can be digital or they can be analog. So the ones that we use, like to detect, if I've got any blood clots in my leg, of course, those would be analog, right? Digital would be, we're just going to look to see if something's at a certain height or a certain speed. Ultrasonic sensors, we can design these things to do check distance, movement, level or solids or liquids, and speed and direction of something. But what the problem we have, and we found this out, of course, in the design of airplanes, so we can design airplanes that are almost invisible to radar, just because we changed the what? This guy right here. I changed the shape and the density of the surface of the airplane. Yeah, I think the B-1 bomber, that's a big old plane. I think it returns like of a bird or something like that. That's all the return they get off it. So these are just some ultrasonic sensors. This is kind of like the one we have on our Amatro line. So it looks a lot like this. And this is a shielded sensor, right? One that's shielded. Yeah, the threads go all the way to the very. Now this is the one that you run in most often when you go into a hospital. Ultrasonic. This is the one, and we're using a lot of ultrasonics now on automobiles. To see if somebody, to sense if you're fixing to run into the back of somebody, or my wife's got one on her van. When she backs up and she's going to fix to hit somebody, it starts going on. Yeah, you can see these little round circles on there. Those are usually ultrasonic. Yeah, little round circles. And now you see them on side of cars. So she's got that on the side of her van. So if we're beside a car and it's in the blind spot, vans have blind spots. A light flashes and the big arrow comes up on her side mirror that says it's there. And my wife's is not a new van either, so it's been around. So this is the ultrasonic sensor that we have on our Amatro line over there. So this is it right here. Oh, this is a Word document. I was thinking it was PowerPoint. Sorry. So what this guy is doing, the way it works, this is a diffuse sensor, photoelectric diffuse sensor. What it does is when the block sets down there, it's lined up. So the blocks we have, I can go right here. Let's just go to the one show. So the blocks that we have, if you look at it one direction, they'll have two holes in it. And this is where the air, this is where the air goes out. And if you turn it around, it has one small hole at it. If you turn it around the other way, it's got a nice big hole going through there. And the ultrasonic sensor is set up, that photoelectric sensor is set up so it'll shoot down this eye. So what happens if it's around this way, it'll hit up here and it'll bounce back. If it's turned this way, it'll hit over here and bounce back. If it doesn't get reflection because it's shooting in the hole, it knows the block is oriented right. So if it sees this, it'll reject it. If it sees this, it'll reject it. If it sees that, it knows you turned it in. And then what it's got over here, so this guy right here is measuring the height of the block to see if it's okay, and it's an ultrasonic sensor. And what it's got a metal tab on this side that you can't see, and there's a inductive sensor on this side. So when this thing moves, and there's the inductive sensor right there, I'm sorry. So when it sees that inductive sensor, when the inductive sensor goes through, it checks the output of the ultrasonic sensor. If it comes back and says okay, then it goes back. If it comes back and says no okay, it means the block is either too short or too high. So here we're combining sensors to produce automation, right? So this guy, the programmer controller, knows if the block is in there oriented right, and now it knows if it's the right height. If it's not oriented right, or if it's not the right height, then what happens is this cylinder right here extends and pushes it into this guy. If it is the right height, then this cylinder right here, this little cradle raises right here, and this cylinder right here extends and pushes it onto the next line. And then here, this is a It's either a reed switch or it's a Hall effect. We could look at the diagram, and this tells the PLC if the cylinder's fully extended. So this is our ultrasonic sensor. This is a digital sensor. It's either a what? It's either a no or no-go. So what we do, we set what we call the span, which means we set an upper limit and we set a lower limit. So if it gets above the upper limit, it says it's bad. If it gets below the lower limit, it says it's bad. And if it's in between, then it says it's good. And that, if you ever look at those blocks, guys, we're talking maybe 2 millimeters. The difference between the short blocks and the big blocks, which is pretty. So we also have photoelectric sensors that are used to sense distance. Transmits at an angle. So triangulation transmits at an angle and measures the angle of the reflected light to determine the distance. Anybody ever seen this guy? So this uses triangulation. So what it's doing is it's shooting a beam out at an angle, and then it reflects back up into the receiver. If you get the mouse up too high, now I'm up maybe 5 millimeters if I'm that much, and notice it don't pick it up because I'm not at the right what? I'm not at the right height or the right distance. So this is using triangulation. So this is basically the way it works. Here it shoots a beam back, it reflects off, and this could sense 1, 2, 3, 4, 5. This could sense 6 different locations or 6 different distances. This guy is set up to only sense what? Only sense 1. So you can act. I don't know if I can. I'm giving it all kind of problems. I don't think I started my camera up. I'm gonna see if y'all can actually see the angles on this one. So I'm not gonna pass it around. So there it is right there. Can y'all see it's at an angle? So it shoots out the beam, and then it reflects off. If you get it up too high, then what's going to happen? It's going to reflect off and it's going to miss the receiver. So you got to have this at a perfect distance, right? You understand, to make it work. So that would be this guy right here, triangulation, time of flight. So this is triangulation, photoelectric sensors. So if you've ever picked up a mouse and you've been playing around with one of these guys. This one that I got off the internet, though, this is showing it could actually indicate, depending on where the light hits, it would indicate the actual distance, right? So this guy could actually sense 6 different distances. What do you mean by time of flight? Yeah, that's exactly right. So we shoot out a beam of light, it hits the surface like a diffuse sensor, it reflects light back. And if we can time the amount of time it takes between I generate a pulse and how long it comes back, then we can calculate the distance, right? Just like radar, that's the way radar works, that's the way sonar works, right? That's the way ultrasonics works. But instead of using sound waves here, or high frequency magnetic waves, which is what radar is, right? You understand that? So this is time of flight. So speed of light, and that would be the formula, which you don't need to know. We're not going to calculate this because it's not on the sequence. So literally, you could come over here and you could take that formula right there and plug it into a programmable controller, and you could actually do what? You could actually calculate the distance between when you transmit it and when you get it back. So this is what's neat about PLCs. You know, on motor controls, everything does relays, but a programmable controller is a computer. So not only can it do the things that we do a lot with motor controls, it also does math. It does math and it does logic, right? You understand that? So it's a computer. So yeah. So this they're already figured out and using all the math they came up with how far it was and what was that? 40 meters on there. Because this is kind of what the police are using now. Because it's real hard to keep up. It's easy to detect radio waves, right? Which is what? Well, not radio waves, magnetic waves, and that's what radar is. But it's real hard to detect light, right? So they basically have a laser thing they point it at your car, tells you how fast it's going. Ultrasonic detectors. I found out this is what they use over on the tank farm over there in was it Calera? Is it Calera? Columbia? No, it's right down off the interstate. Right out of Alabaster. Pelham, Alabaster. You know the tank?
Sending on the airport.
Huh?
Sending on the airport between all of us.
That is gas, guys. That's not oil. That is gas. So they're not going to use anything electrical down in there to sense its level, right? So they use ultrasonic sensors to sense what level of gas they have in those tanks. Okay. So I should move that slide. Liquid level detectors. We have discrete liquid level detectors and continuous level detectors. So your gas gauge in your car would be considered a continuous, right? Then of course the level detector in your commode would be considered discrete, digital, right? Because it keeps the water running until what? Until it gets up to a certain level. So the ones we're going to use are going to be this. Discrete. So this is one that a lot of people are familiar with. This is what they basically have over in the big water tank up on the hill across the road over here. They just have a float, and when the water comes up, the float comes up and it moves the gauge on the side so they know how much water is in the tank. This would be a photoelectric sensor. Now the liquid that we're trying to sense, this would be discrete, right? This one over the left will be discrete too. And why is that? So what we're doing, guys, and we do this a lot, we call this a sensor, but what we're actually doing is we're combining two sensors, right? So notice on this one, what are they combining? They're combining a float. It's not like a float that you float on in the swimming pool. And then, of course, when the level comes up, it causes the float to go up. And what do we have right here? We have a cam. And when the limit hits, when it gets up to a certain level, it hits that cam, and all of a sudden it trips us and lets us know that the liquid's at too high a level. This one right here is going to be a through the beam sensor. Right? You understand that? And of course, when the liquid comes up here or the material comes up and blocks the beam, we know it's at a certain level. I've seen these used, and they'll have multiple ones up the line, so they don't know it's between. If A is tripped and B is not tripped, they don't know exactly what the level is. They just know it's between there, right? Now these are resistive probes. So what they're actually doing, guys, is they just come over here and put a plus and they put a minus, and then they measure what? They measure the resistance of the liquid. So it couldn't be distilled water. This would have to be some liquid that they understand. In the Navy or the airplanes that I worked out used a probe that was very similar to this, but it was a capacitive probe. So it had an outside plate, and then it had an inside plate, and then the probes were like this, so they look like tubes going down in the bottom of this. Anybody had AC? We had these all, our planes that I worked on, they call them wet wing planes. So that means the fuel, actually it had fuel was in the water, was in the wings, but then it also had a 5,000 gallon tank in the belly too. So anybody had AC? So what's a capacitor? Well, why do we need to get a capacitor, by the way? So we create capacitors on purpose. That's what we did. But what do we need to get a capacitor? I don't know if my camera's still working. I might have killed it. This is what I look at here. This is a shielded probe, so I won't pick it up. So nobody knows in this class it says AC. So no one, you forgot what a capacitor is made up of? What's a capacitor made up of? Huh? Dielectric, which is some type of insulator. Good. So air is a pretty good insulator, right? So air could be a dielectric. In fact, materials are rated according to what they call a dielectric constant, which is basically air. Air has a dielectric constant of 1. And then, of course, make sure this thing's working first. I have to beat up my stand. I need to redo my stand. So we have to have a insulator, and we have to have 2 conductors. That's basically all it's required to make up a capacitor. And then we put AC on them. Capacitors will not pass AC, I mean DC, but they will pass AC. So this is what we call electromagnetic interference. You'll see that, and it's AC's all over everything. So this is my oscilloscope probe right here, and here's my function generator putting out AC. I'm going to try to not touch these guys because it's going to couple through me. And all I'm going to do, there's no electrical connection between these two. You can see what's happening? I don't have a common, right? Don't have a black lead connecting between them. But all I'm doing, and I want to get the black leads out because these would interfere. All I'm doing is bringing these red leads close together. And that's a capacitor. Now what determines the capacitance is what we use as a dielectric constant. So this is the way a capacitive sensor works, guys. So I'm just going to take my hand and I'm going to bring it up to close to those things, and you should see the output change. And that's a capacitive sensor. So that's all you're doing. That's what a capacitor sensor you're doing is you're changing the dielectric, you're changing what we're using as an insulator on how much AC passes through. So we used to take these things down, and then I would get different things, and I would set it on top of that, and you'd see the amplitude do what? Do change. So this is a capacitive sensor. Right? You'll see that. So that means if I can bring fuel up inside this thing, then what's going to happen? Then the dielectric is going to change, and then it'll pass more AC. So that's the way a capacitive fuel probe works.
So if you didn't have a capacitor,
What's that?
what if you didn't have a capacitor? So you gotta have one.
I don't know what you're asking.
Say, it like stores electric charge.
Well, it only stores a DC. It only stores a DC charge. So in DC, a capacitor will store a charge, kind of like a battery, but it only stores a certain amount. In AC, it passes AC depending on several things. It depends on the capacitance. So what we're doing is we're changing what they call the capacitance. So this is not a formula y'all have to remember, guys. So you're saying, well, why are we looking at this? I don't need to know it. Why am I looking at it? The formula is x of c, which is the opposition, is equal to 1 over 2 pi fc. Huh? Yeah. So this is the difference between a resistor. And this guy's gonna. It's called reactance, and it's rated in. Anybody remember? Ohms, because it's opposition, but it's opposition to AC. It's not opposition to DC. If DC sees a capacitor, it thinks it's an open circuit. So a basic saying about a capacitor, it blocks DC and passes AC. And it passes AC depending on this. The what? F is what? Frequency, and then the capacitance. The capacitance is determined by the size of the plates, how close you can get those plates together without shorting them out, and what type of insulator do you put in the center. What's the dielectric constant of what's between the plates. So that means that's what we're doing with a capacitive sensor. So I bring a piece of metal on top of that thing, it would have a different dielectric constant than a piece of plastic, but it picks up both of them, right? You understand that? So this is the way a capacitive sensor works. So what you're doing is you're changing the what? You're changing the dielectric constant. You're not changing the size of the plates. So this is the way our fuel probes work, is when that fuel come in there, even though it had a high resistance, it changed the dielectric constant and it coupled more AC through that. And then they would take that and they would get that would indicate the level of the fluid. And what we did is we had some pointing up, we had some pointing down, because planes do what all the time? And so you wanted to get the right fuel gauge no matter which way the plane was going. And what they would do is they would average all the capacitors together. So no matter how the plane was working, the average would always, because when these started emptying out, the other ones would start doing what? Filling up. And they just averaged all the, and I think we had 6 probes down the wings. And then, it always showed, so you could be flying, you know, at 45 degrees and it would still show you how much fuel you had in the tanks. So I need to add that too, because this is very popular as a level indicator. Resistors work the same way. What we're doing here is this is a rod that's got DC on, so this is a rod that's got DC on it, and then I'm putting liquid in between that. In a liquid, if it's not distilled water, it's going to have a what? It's going to have an R. So this is why when you put water in your battery, guys, you need to put what type of water in there? Distilled water, because distilled water is almost got infinite resistance, right? You understand? So you need to put distilled water in there. So what happens here is when this water gets up in here, it gets an R, right? And so the more you cover it up, the lower the R goes down, right? And the less you cover up, the R goes up. Capacitive probes work exactly the same way, but they pass AC. And what we can do is we have a lot of opposition. This guy, the voltage has to be pretty high because we're pushing through water. Here, all we're trying to do is trying to get a voltage through a dielectric, right? You understand? We're not trying to get a lot of current out of it. So the advantage of using these capacitive fuel probes is the voltage is very, very small, and you got no current, almost no current. So you don't have to worry about fires, even though they think. I don't know if y'all remember the 747 that everybody thought was shot down, taken off out of New York, and they finally realized that there was a short on one of the fuel cells, and it blew up, blew the plane up. Y'all remember that one? And they were showing the trailer. They looked at people thought they saw a missile flying up on the back of it, and they deliberately got that big old fuel tank out there and put it out in the desert and recreate it, and that thing did blow up. It was very interesting, which is very unusual because usually the opposition is really, really. Okay. So the level detectors that we're going to use, and we're going to simulate the levels, by the way. So let's go back and get. Let me pause this and let y'all can come back and get y'all one and get recorded. So this would be a float, right? This would be we didn't talk about that. Of course, we haven't got to pressure sensors yet. So what's the difference between a pressure and a force? Huh? Well, does voltage do work? Now, we can't do work unless we can have voltage all day long without work, right? Because what's our work in electricity when we talk about work? We pay for work every month. We call it power. So what's required to get power? Got to have current, right? So you can have current, you can have voltage without work, but you can't have current without work, right? Because you can't have current unless you have what? Voltage. So we do that all the time. So when I go over and flip that light switch off over there, I get no work, right? I'm getting no work out of this. I still have voltage over there on that switch, right? Everybody understand that? So what's the difference between force and work? I'm sorry, what's the difference between pressure and force? Well, pressure is a difference. For pressure, a voltage is pressure. It's a difference of potential. Right? You understand that? Force is something that would make things change directions or move. They don't have to move. It just has to move. So I could have pressure without force, but I can't have force without pressure. So that's like voltage. So I can have voltage without current, right? But I can't have current without what? Without voltage. So the formula for a force, so we can't have force without pressure. That's that, right? I don't know where that pen came from. Yeah. So force, I don't know what I'm doing here. If I can get this to draw. There we go. So force is equal to area times the pressure. And what's work equal to? Huh?
You want the actual formula?
Yeah, it's force times distance or speed. So this is the way so that's our formula. We say power, which is our work, right, is equal to force, which is what? The voltage, right? Times the what? Times the distance. Or times the speed, which is current. So if I go over and push against that wall, do I get any work? Am I doing any work? Am I generating a force? Yes. Right? But no work, because I don't have what? My distance. So what we have here is we have a pressure sensor, which we'll get to later on. And when we come up here, everybody's going to the water center later, right?
Going on the water?
Yeah. Go, when you're out swimming. Hopefully. When you go underwater, the deeper you go, you feel more what? Pressure. So that's what they're saying here, is they're saying, okay, the higher the level of that liquid, the more pressure it's going to generate at the bottom. So I've seen guys, they actually do, huh? Okay, so let's think about a piece of steel. And I've got it so high, I got it like this, right? So water has weight, air has weight. Then I got this weighs 100 pounds. Then I go over and make it twice as big, it's going to weigh what? 200 pounds. I go over and weigh this. So water has so much weight per square inch. So water is a liquid, but it has weight, right? You understand? So the higher the column is, the higher the piece of steel is, the more it's going to do what? The more it's going to weigh. Right? You understand? So this is why you see these guys go, these deep water divers, they're in pressurized suit, right? Why? Because they got to equalize the pressure between them and what's trying to collapse them. So the higher the water, the deeper you go, the further you're under that column of weight, right? You understand? And so what happens is you feel more pressure. Air has pressure to it, right? What's sea level? Air pressure at sea level? Y'all don't know the air pressure at sea level? Huh? 14.7 psi at sea level. You start going up, and what happens to the pressure? Because you're getting higher. The column of air that you're under keeps getting smaller, so the air pressure goes what? Goes down. And it gets so low that people on the mountain can't boil water. I mean, they can't boil water because they don't have that pressure on the top of it. So instead of boiling at 212 degrees, it might boil at 30 degrees.
Really?
Yeah. And then it'll turn into vapor. So it's real hard to boil water at high pressure because it boils at such a low temperature. So 212 degrees is at sea level. So that means the higher this column of air is, the more pressure is going to be felt what? Down here. And then we can translate that pressure into what? Into a level. If you know the pressure being generated by your liquid like air. So for years, that's the way we sensed the altitude of an airplane. That's before we had all this Doppler and everything. We just measured the pressure of the air. The pressure of the air outside the plane. And it was on the side of the plane, and they displayed that as altitude. And that's all they was doing was measuring the pressure because they know the weight of what? They know the weight of air at sea level. And if you know the weight of air at sea level, then you can calculate what that pressure would be. So airspeed. So we use airspeed. That's all we do is we just jam air into a PDOT tube in the front, right, on the side of the plane. And then we compare that. They compare it to static air on one side. My wife just took my car. She stole my car. We compare that to static, and they use that to calculate airspeed. And angle of attack. Y'all heard about the angle of attack sensor, right? Y'all hadn't heard? The 737s, y'all hadn't heard about the 737s? Crashing? The 737 MAX crashing? Because of the angle of attack sensor?
Is that the plane that's been crashing?
Yeah. So angle of attack is basically the orientation of the plane to keep it oriented. So it's how it's nose up. So nose up would be a positive angle of attack. Nose down would be a negative angle of attack. And what happens is that if you start stalling, what they want you to do is they measure the angle of attack. And normally if you start stalling at a certain speed, you want to drop the nose of the plane down, right? So what was these planes doing? They had a faulty angle of attack sensor. The plane thought they were fixing to go into a stall. What did they want to do to pick up airspeed? Drop the nose. And what did they drop the nose to? Into the ground. Because it happened at takeoff. And, you don't have much time to think. I think Maurice brought up the stack. Don't they get trained in that? But, man, it's just like you go out here and you drive 10, 15 years, and then you get out there and something happens, and you just don't have time to do what? Yeah, you're into a tree before what? And you're sitting there saying, I'm fixing to hit that tree. What do I need to do? So these are capacitive sensors. These are nothing but strain gauges, guys. Load cells mounted under here. So here they're actually, instead of measuring the pressure, they're actually measuring the weight of the material. You see these used all the time. I mean, I've seen these measure the level of cold. I've seen it measure the level of slurries. I've seen it measure the level of all type of things. All they do is they empty out the tank, they zero out the scale, and then from then on, they know exactly what they got on if they know how much so much weight of the material. I told you about the counting scales, right?
Was that you talking about somebody put money in something and win it? There was some class I was in. I think it was this class. It said somebody they was counting money and they weighed it in a scale. Was it this class?
No, we used to do inventory. We used to rent out what we call counting scales. But all they would do is they would take a bag and they would put the bag on there, and then they would zero out the scale, and then they'd put like 100. So they'd count 100 of them, and they'd put them on there, and they'd say, okay, this is equal to 100. And then the scale would do the math and say, well, if this is equal to 100, then 1 must be equal to this. And you could literally take one of these little, like a needle. So we worked with a place over in Florence that they made medical supplies. And they used to measure their scalpels and everything. It was so neat. And they'd go in there and they'd take one and throw it on that scale, and then they'd count one. And that was doing it strictly by what? By weight. So we used to rent out accounting scales when they went to inventory, but we had some companies that used them all the time. You know, just to do what? Just to count. Make sure what they were putting out, what they were putting in. So, it wasn't money, but you could count money too. Money counters do a lot like that, where they're just measuring the weight. So a quarter has a certain amount of weight, and a nickel has a certain amount of weight, a dime has a certain weight, and a penny has a certain weight, right? So you can take 1,000 pennies. If you knew what 1,000 pennies weighed, usually you want to do a lot of them so you get a really good average. Then you could count pennies or dollars or not dollars. Dollars are real hard. But so yeah, I've seen money counters that count on nothing but weight. They'll take a big old thing and fill it up. They'll zero it out for what they're putting it in. They'll put all that money in a tub, put it on scale, and it tells them exactly how much they got in. And then of course ultrasonics. Is this all of them? This is all of them I know of. But is this that don't mean anything. I don't know everything. You might run into some other type of level sensor or something out there, you know, that you might not, that we might not talk about in this class, but at least you know what a level sensor is, right? Are we okay on that? Any questions? Huh? So these are the next group of labs that we're going to be working on, and it's going to be 3 labs just like that, and we'll run those off and give them off at the next lab session. What we're going to try to do now is going to try to get through with the labs we're working on that. Everybody okay?
What does the lab do for building our own circuit?
It's due when you get through with it.
Oh, it's not, we don't have a due date to it?
Now, we don't do due dates in this lab because it's hard to do it with this because different groups work at different speeds. So it's like motor controls. So we didn't have any due dates on motor controls. We're not on this. It's just that if you know you only do one lab, guys, you know you're not going to do real well, right? So your lab grades is based on quality, and it's also based on what? Quantity. And then, of course, being safe. So you need to do them as fast as you can, but you need to do them right? You understand that? Okay? Any questions? We okay? All right, somebody turn on the lights and let's go to lab.